Hello statistics class, we're going to look at another example following up on inference after our first quiz here. So this is the handout chapter 20 quiz C, and it has some additional notes on it first. But first let's just do another hypothesis test. So read through this, pause the video, and then we'll pick up. Alright, so basically in this one we have an explosive detector. We've got 4 boxes, and we've run 50 trials of trying to find the explosive that's in one of those 4 boxes randomly. And our detector has detected it 16 times. You might be thinking, oh God, we're all going to die because it didn't find it, 34 of those times. So that's definitely a wise cautionary concern there. But we want to just say, is this at all effective at all? In other words, do we have evidence that something beyond just random chance is happening with this explosive detector? Because it might just be like our first line of defense. Then we have another detector of a different variety, or some dogs or something like that. Okay, so do we have that 16 just because of random chance, or is this detector actually doing something at least? So we're going to test a hypothesis and go through that process. So let's have a look. Alright, so first I think we want to employ some good hypothesis test procedures. I should always see what you know. And I think just about everybody did that. So let's get what we know here. So I'm just going to start looking at what I know. So, oops. Hold on. So what do I know? I know that n is 50. I know that p, the standard of that we're going to check against, what do we think p is to begin with? Well, lowercase p, thank you. It's 1 out of 4 times, right? So it's 0.25. That would be just a random chance of detecting the bomb. And then we found it 16 out of 50 times, so p hat is going to be 16 out of 50. I put that in my calculator and I got 32%. Oh, there we go. Okay, so that's what we know. Let's also talk about our population of interest. A lot of you skipped this on the first quiz as well. It's uber important that you think about what your population of interest is. You might not know it exactly at the beginning, but you need to think about it, and as you go throughout the problem, narrow down exactly what it is, even if you don't exactly know for sure until you're interpreting the results of your test. So the population of interest here is big time important. So what are we thinking about? What do we want to extend our results to? We're checking for bombs in boxes. So if you put boxes, I think you'd be okay. In class today, I think we had a couple better ideas than just boxes. We said containers, maybe all containers that could have a bomb. So you might not even be exactly right about this, but it's very important for the process of getting things into your head correctly that you go through trying to figure out what's the population of interest. Okay, so now we're going to check our hypotheses. So let's do that. So I'm going to go like this and say H sub O. So what is our null hypothesis? Well, we're going to assume that the thing is just randomly not working, or in other words, detecting the bomb only 25 out of 100 times, or 1 out of 4 times to begin with. Our alternative hypothesis is going to be, of course, that something unusual is going on. So H sub A is going to be that P, we could do a 2-tail test, a 1-tail test. What do you think? Well, I think we're not really interested if it's extremely unlucky. So I think this is a 1-tail test. We're looking at, does it detect the bomb more than 25% of the time? Okay, you have 3 assumptions to go through. I think everybody was doing pretty well on those, except for maybe the 10% one on the last quiz, so I'm just going to leave those out. So you want to check, is it random? Yeah, they said it was. Are the trials independent? Well, you've established that it's random, so you just need to check the 10% thing. So could we perhaps look at more than 500 boxes? Yeah, we could, and check in P and NQ are greater than 10, which they are in this case. So our assumptions are good. Let's focus on our statistics. So I'm going to just draw this out on this one. So our test statistic down here. So a lot of people on the test did not put what equals. Well, we're going to have T, we're going to have Z, and we're going to have another symbol. So make sure you write what that test statistic is, Z for now. then it's the test statistic p hat minus p over, we should have parameters when we do our hypothesis test, so instead of p hat I should have p and q down here. I think everybody was good on that. Just reminding you. So we're going to have 32% minus 25% over the square root of 25% times 75%, all divided by the 50 was our sample size. Okay, so put that in your calculator, get your results. I got z was 1.14. Okay, so that's not my p-value yet, so now I need to go and draw a picture to find my p-value. Make sure you draw a picture. Several people didn't, and that's why they screwed up on their p-value. So don't be lazy here. This is important. This picture is not something I'm forcing you to do. It's something that you need to do so that you never make a mistake. So here's my z-curve. I've got my p in the middle, like we talked about in that last video about our quiz. We're trying to see how unusual this p hat measurement was. It is 32%, right? So it's out here. So how unusual it was. Did we do a 1 or a 2-tail test? Well, right there it says 1 tail, so we're looking at greater than, and also it says greater than, so your picture should match that hypothesis that you chose. If you chose not equal, then it should have this over here as well for 2 tails, but we don't have that. So we're going to go to our table, look up the value for 1.14. I know you guys are experienced at that, so I'm not going to flip to that page. So I already did it, and I found the table told me 0.87. Remember, the table always references below that point, so you've got to go complement 1 minus 0.8. That's an 8. 7. So this guy over here, and by the way, clearly that guy over there is not 87%, right? It can't be. That's one of the reasons we use our picture, so we don't forget about this complement part. So it's going to be 0.13 or 13%. So let's write out our conclusion to finish this hypothesis test. So remember, we're going to refer to what we talked about in the last video and make sure that our conclusion follows one of these two forms right here. Either I reject H sub O or I fail to reject H sub O. One of those two things is what we want to do. So in this one, well, do we have a large or a small p-value? I didn't even establish an alpha level. I don't have to. It's a good idea to start thinking about doing that, but what's most important is the p-value. So that's a pretty large one, 13% chance of seeing what we saw. That's a pretty good chance. So I think I'm going to fail to reject. So since my p-value of 13% is fairly large, I fail to reject H sub O. There is insufficient or not enough evidence to suggest that. Now let's go back and look at our population of interest. So if I had my assumptions here, that would also be some help on my population of interest. Is this good? But there's insufficient evidence to suggest what? We assumed the bomb wasn't doing its job, basically. That's what this is. You could even write that in, and this was the bomb detector is detecting at least some bombs. So, you know, detecting at least some bombs, yeah. So there's insufficient evidence to suggest that, I guess you could put this if you want, H sub O is false, or that the bomb detector is actually detecting more bombs than simply due to random chance, random variation. Okay, so there's my context. You definitely want to make sure you're real clear on that context and how to write a conclusion for a test. That's the most important part of the whole thing. Okay, so before we end this video, I wanted to go over a variety of notes. So let's go down here. I think you should have these on your handout form as well. So some of these came from the teacher manual. And I think this first few just discuss this example we just did with the bomb detector. So it says on quiz C we looked at the test of a sensor. We test it by hiding explosives in the boxes. Okay, so pure guesswork says 25%. Somewhere above there's a level of experimental performance that would convince us that the sensor works, giving us something like 20 out of 50 or something like that. Finds. Even someone operating an ineffective sensor, of course, might get lucky just due to random chance and make some correct identifications. in which case we'd be using a worthless device. So thinking we're safer than we are in fact thinking we're safer when in fact we are not is the consequences of type 1 error here. So let's remember what a type 1 error is. You should just have that in your head. So type 1 is rejecting, that's the thing, the way I'd remember it, rejecting H sub O when it is actually true. So they're saying in this case, thinking we're safer when in fact we are not is the consequence of a type 1 error. Let's just go back to our hypotheses up here. So our hypothesis was the sensor is not working, it's just detecting it 25% of the time. So it might have been a good idea to write this up here. And this is the one that is working. Just to clarify for yourself. You don't have to do that. Make sure you get a nice parameter symbolism in your hypotheses, but that can help too. Okay, so now they say, suppose the sensor actually does work, that it can detect explosives at least some of the time, maybe 50% of the time. That's pretty decent. Might not be good enough for us, but it's our first line of defense. When we run our test, it might actually succeed in only 19 out of 50 trials and end up failing our hypothesis test by not quite reaching our alpha level if we decided it was like 1%, because this is a high sensitive situation. So in this case, we might overlook the usefulness of a device. That would be the consequence of making this type 2 error. Okay, so I really liked this because it really, I think, made the power issue a little bit clear. So the power of a test is its ability to spot the fact that the sensor works if it does. So note that the better a sensor is at spotting explosives. So if the true success rate is 80%, the more likely we are to notice. So power increases with the size of the effect. I just wanted to do a little bit of a drawing here to clarify that issue. Effect size is one of the things that affects power that you should be pretty clear on. It's not a big deal. So let's go back here and grab our drawing tools. So effect size is something like this, right? Here's our Z curve. So if the true thing is here, and what you measure is way up here, and they're fairly different, in other words, this distance, if that's a large distance, and they're very different, then you're very likely to see that they are in fact different, because the p-value produced will be pretty small. So you're probably going to reject, and it's probably not actually the case that they're the same, so you should have rejected, hence making the power of your test high. So that green line I drew there, that's the size of the effect, or the effect size, in other words. If, though, oh, it doesn't want to let me take it back. If, though, your p hat ends up being right here in your sample, and they're very close together, then the effect size is quite small, and you don't have a lot of power to reject, because you're probably not going to reject, even if they are in fact different things. Now, of course, in this case, if they're that close to begin with, we probably don't want to reject anyway, because our sensor's not working very well. Oh, and I should have, if the sensor's working, then I should have put it right here, right on that side, not over here. So our effect size would have been this distance, but the same argument applies, okay? So in that case, the sensor's not working very well anyway, so we probably wouldn't want to reject, so it's not as big of a deal. But the effect size is one thing that affects power, and it's kind of outside of your control. So let's see what else they say. How can we avoid putting our faith in a bogus sensor, a type 1 error, because that would be probably the worst consequence in this situation? Well, they said we can demand a higher standard of proof, in other words, a smaller alpha. So that's something that we do have control over. Remember in this example, I didn't even pick an alpha to begin with. So if I'd have picked an alpha of like a real loose alpha of 10%, I still would have gotten lucky and failed to reject in this case. So that would have been a good thing, because we don't want a type 1 error. But if I had picked 5% alpha and demanded that I have even more proof that the sensor is working, of course I still would have failed to reject. If I picked a 1% level, I still would have even stronger decided that there's definitely nothing unusual here. This thing is definitely not working. So we can pick a smaller alpha to avoid this type 1 error. But making the test harder to pass makes it more likely that an effective sensor will fail to impress us. So this, of course, increases the chance of a type 2 error and reduces the power of the test. So I think this one's a little bit more subtle to understand, but this is a great example. So read it back to yourself a couple times and see if it makes sense to you. So I think the weird part here is the way that alpha works. Remember, alpha has values like this. Let me get my draw tool back out here. So alpha has values like this. Alpha could be 5%. Alpha could be 10%. Alpha could be 1%. So if we make alpha smaller, in other words, if we go from here to here to here, then we're decreasing the chance of a type 1 error because we're demanding more proof. We're increasing the chance of a type 2 error and reducing the power of the test. Because remember, alpha is the chance of rejecting alpha is the chance of rejecting a true H sub O. The power of the test is the chance of rejecting a false H sub O, like of course you want to have happen. So I think that you just want to think about this for a while and until you get it straight. So because this is an important one and it's a little bit sneakier. So increasing alpha, if we go the other way, we take back my arrows here. Let's see if it'll let me do it. No, it doesn't want to let me do it. So let me get my eraser. Oh yeah, that works nice. Didn't know about that. So if I increase my level of alpha, if I in fact loosen up my standard of proof and I go from 1% to 5% to 10%, yes, I increase the probability of making a type 1 error and rejecting a true H sub O, but I also increase my power. And I think the reason for that, you should understand, is power is a rejection. It's rejecting when you should reject. So even though you increase the chance of making a type 1 error, you also increase the chance of actually making the correct decision and rejecting something that's false. Okay? So I think that's the easy way for me to understand that. Anyway, of course, I think the last thing that affects power that's super simple is raising n gives you more power because you can see more of what's actually going on. That's pretty simple. I don't think anybody has trouble with that. All right, so we have some other notes here I just wanted to go through, and let's see how long it takes. So these are all things you just want to read through carefully. They're nice supplements to chapter 21. So it says we don't spend any time here calculating power or the probability even of a type 2 error, in other words, calculating beta. You won't need to do that on your AP test. So that's really important that you understand that that's not something you need to be able to do. You just need to understand it conceptually a little bit. These calculations are difficult. I will be, hopefully this weekend, making a video explaining that little power diagram in the book, which I think is one of the hardest diagrams in the book, so you can look at that. I really recommend that you do. But you realize that you don't need to worry about getting beta or power for the AP exam. The next note here is it says, although we do talk about alpha levels in more detail, we want these to continue to provide general guidelines rather than firm decision rules. We'll stick to reporting our p-value in order to actually make the decision. I really agree with the book here. You want to think about the p-value because it's the probability of seeing something that you saw, or even rarer. In other words, it describes in a finite sense, a very numerical, black and white sense, how likely it is to see what you saw and whether or not that assumption was right. In other words, whether or not the null hypothesis was right. That's very clear. Picking an alpha is the only thing that really matters for us is the type 1 error. All right, the next note is several times in this course we've encountered words that don't quite mean the same thing in stats as their normal, colloquial, everyday usage. So significant is a big example of that. When we say the result is statistically significant, we mean it's unusual. So unusual that we have to reassess our assumptions, those ones, in fact, that we made in our null hypothesis. So I think that that's really good. Without enough data, we might not be able to detect a minute change, for instance, if we're talking about teenagers smoking, but we might not think that change is of practical importance. So really the issue here that we want to be clear on is that practical significance and statistical significance as measured by, for instance, p-value. That's what we're going to focus on this year. Can't, of course, spell significance. Ha! Significance. There we go. Are two very different things. In a lot of problems, we're going to, of course, start out by seeing if a difference is statistically significant, and then we might have to think about, well, is it statistically significant enough? Or in other words, is it different enough to be practically significant? These are separate things, so make sure you're clear on that. All right, let's see. Use a confidence interval to expand your conclusion. We did that on the first quiz. So after saying there's strong evidence of a difference, if you have that difference, you might want to follow up by saying, okay, if there's a difference, if the null hypothesis was false, let's try to estimate what the real thing should be, try to estimate the real parameter using our statistics, and create a confidence interval. That's a great thing to do. And the last thing we want to talk about is, instead of finding a p-value, actually use a confidence interval to evaluate the test. We also did that on our first quiz. This should be familiar. You can definitely do that. And you guys all did pretty well on that. So if the hypothesis value is not in the interval, then what we saw casts doubt on the model, and we're probably going to want to reject. If it is within it, we fail to reject. We've done that before. I think these last couple notes are of particular importance to us. So it says a cautionary note, confidence intervals and hypothesis tests for proportions are not quite equivalent. When we do the standard error in a confidence interval, so this is for the confidence interval, we have a standard error. We have statistics in here in P and Q, right? And that's what we use when we go the confidence interval equals P hat plus or minus some Z star level times this thing. So we put statistics in there. When we do a hypothesis test, we start by assuming the null hypothesis is true. So in our hypothesis test statistic, where we go statistic minus parameter over the standard deviation, we're not putting the standard error in up here, we're putting this guy with the parameter and the parameter because we're checking to see if we believe that parameter, so that's what we're going to use for our standard deviation. Over here we have a standard error for the confidence interval. For the test statistic we have a standard deviation. I think this matches up very, very well with what we saw in the last video at the very beginning, this fourth note. Confidence interval should only contain statistical values, things like p hat. Hypotheses should only contain parameters. That also applies to the mechanics of a confidence interval or the mechanics of a hypothesis test. So I think that that's really key here. Those are, of course, going to be pretty similar in most cases, but if your effect size is really large, there can start to creep in some differences that will mess your results up. So I'll see you next time. Hope you found some of these ideas illuminating.